In the previous lectures, we examined the dynamics of a single rigid body with no external forces. In this short video, let us just consider a few different configurations of single and double pendulums, but now in 3D and now consisting of 3D rigid body objects. Obviously, we've simulated single, double, multiple pendulums in 2D, but let's see how we would do something like that in 3D. Okay, and sort of understanding how to simulate objects like this in 3D is more or less most of what you want to learn to do general 3D multi-body simulations. If you can do a triple pendulum in 3D, you can do 3D multi-body simulations. Okay, so here is a single rigid body, and if the spring weren't there, it's basically the same as a free spinning rigid body, maybe with just gravity acting on its center of mass. But if a gravity acted on the center of mass, it will affect the linear motion of the center of mass, but not affect the rotational motion of the body itself. In any case, if you attach, let's say, one end point of this cuboid to a spring that is connected to the ceiling like so. So what's the free body diagram for this? We have gravity and then a spring, and the spring exerts a moment about the center of mass, and that can affect the rotational dynamics of this rigid body. So we will do a whole lecture / video simulating, writing equations of motion and simulating this system. So perhaps this is the simplest kind of pendulum to simulate in some sense. Maybe the most direct analog of a simple pendulum or even a compound pendulum 2D to 3D is a 3D rigid body version of that, where you have a 3D rigid body and it is attached to the ceiling, let's say, at a single point. And the point corresponds to what would be called a ball and socket joint, which is, you can think of it as a point that does not constrain the rotation in any way, but constrains the translation. In other words, that point is fixed in space, but no constraint on the rotation. So ball and socket joint is just something that allows 3 degrees of freedom here. So that point cannot move, but you can move, you can rotate in any direction. So you can imagine sort of the inverted version of that, where you have a point that is fixed and you have this rigid body contacting that point with no slip. There is no slip of this point or movement of this point, let's say. And this rigid body could be spinning or have essentially some angular velocity. This system would is analogous to what would be called a top, a children's top, which is a very classical problem. Usually we consider an axisymmetric version of the top, but you can imagine not axisymmetric versions as well as here. Okay, so this problem is qualitatively different from this problem in some sense. And then we can imagine a double pendulum, but made out of rigid bodies. So you imagine a rigid body and then a massless bar that connects this point and this point, a massless bar or a taut string, so that this length does not change. And then we have a rigid body, and this point is what we would call a ball and socket joint again, and again ball and socket joint, where it can rotate in any direction, but this point cannot move. Similarly, these two objects can rotate relative to each other however they want in this about this point, but this point itself is coincident between these two rigid bodies. So that's another kind of pendulum. You can think about how you would simulate something like this. Yet another kind of double pendulum is maybe the most sort of direct extension of the double pendulum in 2D, which is two rigid bodies, both having mass and so on, mass and moment of inertia. And then each of these rigid bodies is connected to each other and to the ceiling by a ball and socket joint. In other words, again, these two rigid bodies can rotate relative to each other, but in any manner except this point needs to be common and coincident between these two rigid bodies. Same between this rigid body and the ceiling. So how do you simulate that? Um, so that's a simple kind of double pendulum. We can imagine other kinds of joints instead of a ball and socket joint. So imagine, for instance, this kind of a pendulum where you have a ball and socket joint here, but a hinge joint here, right? So ball and socket joint allows 3 degrees of rotational freedom. A hinge joint allows only 1 degree of rotational freedom, right? So this is like the human elbow or a door hinge, right? So that door hinge usually has just 1 degree of freedom. In other words, you can rotate this object relative to this object about this axis, right, out of plane. So how do you simulate this system? This system, of course, has 4 degrees of freedom. This one has 6 degrees of freedom, right? So this number of degrees of freedom equals 6, because this has 3 degrees of freedom relative to this, and this has 3 degrees of freedom relative to this rigid body. Each rigid body has 3 degrees of freedom here, 3 rotational degrees of freedom. This one, something to think about, how many degrees of freedom this object is. It depends on how you want to write the equations of motion, whether you want to consider this to be a rigid body or not. But I guess I'll let you guys think about it. These things have rigid body number of degrees of freedom equals 3 because this is a rigid body. A single point is constrained to not move, but so you start out with 6 degrees of freedom for a rigid body, and you're left with 3 after you constrain 1 point. This one has the full 6 degrees of freedom because this rigid body can translate and rotate however we want, and the spring does not really constrain that. Okay. So if you want to think about this, maybe you've thought about this. So you can think of this rigid body as starting to have 6 degrees of freedom. So it's 6 for the rigid body minus the fact that this point is connected to this point by a rigid rod is actually 2 constraints, right? So it's actually saying this point is at a constant distance from this point. Sorry, that is actually 1 constraint. So that's 5 degrees of freedom. Okay, so we just talked about the hinge joint. That's 4 degrees of freedom, 3 degrees of freedom here, plus 1 degree of freedom here. Another kind of joint is what's called a universal joint, which has 2 rotational degrees of freedom. So a ball and socket joint has 3 rotational degrees of freedom. A hinge joint, also called a revolute joint. So in robotics, a hinge joint is often called a revolute joint. Okay. A universal joint has 2 degrees of freedom, or allows 2 rotational degrees of freedom. This picture sort of shows it. If you have a rigid body like this and a rigid body like this, and imagine sort of a cross-sectional plane here, and you draw these 2 axes in the plane and z out of plane. The 2 rigid bodies can rotate about the x-axis, the y-axis, but not the z-axis, right? So there is no this sort of twist degree of freedom, but you can rotate this rigid body about the y-axis or about the x-axis. That's basically called a universal joint. Um, it's usually constructed in this manner, at least. So I'll let you guys look up online pictures of this object. But this is an implementation of a universal joint where you have like a plus shaped object like this, and we have this rigid body, so one rigid body like so, another rigid body like so, that are connected through this another rigid body, which you can think of as being massless. And this green rigid body can rotate about the yellow rigid body about this axis, everything else being fixed. And similarly, this orange rigid body can rotate about the yellow rigid body about this axis. So effectively, this green rigid body can rotate about the orange rigid body either about this axis or this axis, basically having this intervening massless rigid body between the green rigid body and the orange rigid body allows you to have this 2 degree of freedom rotation. So that's called a universal joint. Um, okay, so what we did in this video is just go over a few different configurations of pendula and double pendula with different kinds of joints. The intention is to just show the variety of possibilities, at least some variety of possibilities, and you should be, at the end of this course, be able to simulate any one of these systems confidently, and that's our goal. And you will notice that the methods that we use for solving all these things are relatively the same.